have done the...
Só um minutinho que não começou.
Ok.
Agora tá, beleza.
Okay, so we have done the geological model, we have done the upscaling model. Now I'm going to talk about flow simulation. Maybe in the posterior classes, the things that I'm going to talk here, people are gonna talk about it again, some steps, okay? So I'm gonna make some kind of resume here because it's quite important to this integration in between the flow simulation and geological model. So it's only a resume here, but I think that in the forward class, some things here like formulation in the dual porous reservoirs, my colleagues will gonna talk about it again, okay? However, in this stage, I'm gonna talk about uncertainties because until this step, I never talk about uncertainties, what kind of uncertainties that we have, which are the probability distributions for each uncertainty. So I'm going to talk it about now, okay? So in the CLEC cluster reservoirs, normally we have a single porosity models. Why? Because it is the single porosity model is the conventional model in flow simulation. So normally in flow simulation, we use single porosity models. So it is only a grid where you have a porosity, where you have only one permeability, where you have only one net loss. So this is enough to characterize normally conventional reservoirs. However, in carbonate reservoirs, you can also use single porosity models, but you can it is quite common also to use dual porosity models, where you have a fracture system and where you have a matrix system as in conventional reservoirs. So how does it work in a dual porosity system? So in a dual porosity system, so you have two grids. So for each block, you have two. So this is so you have a fracture block and you have a matrix block. So you have two superposed grids, okay? So in the dual porosity system, that's why the reason it calls dual porosity system. But you need to have a matrix to fracture exchange fluids, okay? Because if you have two grids, how these grids are related to each other. So you need to have a term that represents the fluid exchange between the matrix and the fractures. And what is this figure in the left side? This figure in the left side represents how does the flow simulator sees your fractures that you're gonna input in flow simulation. So for each block that you have in flow simulation, you have a kind of this idealization to represent the fluid exchange between matrix and fractures. I call it this idealization because the bibliographic reports call it this as idealization because this is how simulations see your fractures. So you can input a very heterogeneous fracture network and simulator will gonna see that like this. However, you don't see in a flow simulation this Sugar cube that is called also in bibliography. You don't see, you only see this, but this is how the mathematical transformation that this is how the simulator sees your matrix to fracture transfer fluid, okay? So you have a lot of matrix, a lot of fractures here that could be horizontal and vertical, that could be that they are vertical and or horizontally for each block that you have. So the number of these fractures that you have, it's related to the fracture spacing, okay? So the increase in fracture spacing, you have less matrix blocks, okay? So this is a kind of idealization. And you can study, there are a lot of reference that shows how does it works, okay? But the most important is this side, okay? That you have two grids. fracture cell, matrix cell, and we have a term that is the matrix to fracture transfer fluid term. I'm going to talk about this formulation, okay? So inside each block in the dual porosity flow models, the simulator sees our geological characterization like this. So this is a huge transformation because we lose a lot of data that we have characterized in geological model, like different fractures in different scales with different permeabilities, and then the simulator sees your fracture network like this. So a very uniform, continuous and parallel fracture system, okay? So this is a huge transformation. So it is normally expected that we lose a lot of representation when we carry this data from geological models to flow simulation, okay? So the fractures are aligned according to grid orientation. The material, so the material in matrix blocks are assumed as isotropic. So we have, so each matrix block is assuming to be equal inside the huge block that we have in flow simulation. So the fractures are assumed also as continuous, uniform and parallel to axis. So we have a lot of transformations here, and we know that in reality is never like this, okay? Because we have a lot of fractures are never well orientated, are never well continuous, are never well uniform. We know that. So we lose here a lot of information this carried when we carry this data into flow simulation. So one thing is that in dual porosity models we have the mass. This is the formulation, okay, in flow simulation. So we have the mass conservation in fracture system, and we have the mass conservation in matrix. So the mass conservation in fracture system, so here we have the Darcy law that represents the fluid movement between blocks, the fracture blocks here. Then we have a matrix to fracture transfer term, that is this one, which is described here, okay, which is a function of fracture spacing, that is here, is a function of the volume of the block, so the block size, is a function also from the matrix, the permeability from the matrix, relative permeability, viscosity from the fluid that we have, and the difference between the pressure in the matrix and fractures. Then we have also this one, this is a source term that represents an external source that is a well, like a well that we have. So this is the formulation for dual porosity flow models, okay? So we don't have flow between the matrix blocks in dual porosity models, okay? So that's why we have only these terms. So in dual porosity flow models, we assume that the flow goes first into the fractures, and then it flows into another block that is a block from fractures, okay? But we never have flow between the matrix blocks, okay? So we have flows that the water enters in fractures that it can goes like we can go. We have a transfer fluid between this matrix and fracture term, but we don't have flow between matrix blocks, okay? So another kind of, this is a kind of extension of dual porosity models. We have a called dual permeability model. In this dual permeability model, you have flow between matrix blocks, okay? So in dual porosity models, we don't have, as you see in this figure here, you don't have flows between matrix blocks, but in dual permeability models is an extension of this dual porosity that you have in flow simulators. You have flow between matrix blocks, okay? So that's why you have, again, the Darcy law in mass conservation in matrix, okay? One thing that I forgot to say is that in dual porosity models is a kind of type 2 reservoir. So you have a high permeability in fractures, but you have have permeability matrix, or is very small. So that's the reason that in dual porosity flow models, it is assumed that you don't have flow between matrix blocks. But in the dual permeability flow models, that is that kind of type 3 reservoir that I talked in the beginning of this presentation. Normally, you have higher permeability in matrix. That's the reason you have also flow in the matrix. Okay. One thing that is important is that when we talk about the dual porosity concept, we have a kind of divergence, because in the geological concept, fractures indicate the presence of primary porosity and secondary porosity. Okay, so normally geologists, when they say, "Oh, this reservoir is dual porosity," they say that because we have fractures, or we have caves, or we have vugs. But in reservoir engineering concept, fractures are does not always indicate a dual porosity, the necessity to use a dual porosity flow model. I'm going to talk about that, because we can also use a single porosity flow model in a fracture reservoir. How? You can make some kind of average between the fracture system and the matrix system and use a single block. Okay, so that is some kind of divergence between the geological concept and reservoir engineering concept. So this is a kind of complex image, so that I'm going to show here, that resumes what I was talking about. This guy, Borbio, shows this in a state of art. Is an article that is a state of art about fracture reservoirs. Resuming this is that this article shows that there are three things that are important to see if the reservoir has a behavior as a dual porosity or a single porosity. Because as I said previously, in engineering, so in flow simulation, in reservoir simulation, when we can have fractures, but not necessarily we need to apply a dual porosity model. So this guy Borbio studied the main things that are important to decide if it's a dual porosity or single porosity. The scale is very important. So the fracture scale compared to the grid block, the connectivity between fractures, and the kinetics of matrix fracture interactions compared with the fracture medium flow that I'm going to talk about. And two things that it shows is that the 2 points that it shows that is very important is these two variables. This one is the characteristic time for matrix to fracture transfer. This is a time that represents the time that is necessary for fluid that comes from fractures enter in the matrix block and imbibe all fluid or drain all fluid that is inside that block. It is the time necessary to recover all oil that is inside that block. The other time, it is simulation time step required to describe the flow progress in fracture medium. So it is the simulation time step that describes the flow progress between fracture blocks. Okay, so these 2 times are very important to decide if it's necessary to apply a single porosity or a dual porosity flow model or a dual permeability also. I'm going to show here an examples. As you see here, this is example 1. This is a kind of dual porosity example of a dual porosity behavior. We have the flow that goes very fast in fractures. As you see here, the flow is already here in the second block in fractures, but you can see that the water here that comes from this fracture has entered in the matrix, but it does not has already produced all oily here. So at the same time, the water goes in the next fracture block. Okay, so this is when we compare this with the last slide. this means that simulation time that describes the flow in the fracture blocks is smaller than the time for the matrix fracture fluid transfer, okay? So we have two physical phenomena that are occurring in different spaces for the same time. So this is a kind of example that is very difficult to make some kind of average between these properties. This saturation is very difficult because you already have a flow that is going in this block. So another example that I'm going to show. Oh, okay. This is an example of a refined grid, okay? So this is a single porosity grid, but is a very refined grid to show what is an example of dual porosity. So you can see here, so blue one are the water saturation in fractures. So you can see that water goes very fast in this kind of fractures that has a huge permeability, but you have a lot of green zones here inside the fractures that are not fluid of water. So this is matrix blocks. Now I'm going to show here a single porosity behavior. So, but a single porosity behavior with the presence of fractures, okay? In this case, it's another example. So the water enters in fractures, okay? But you can see that the matrix is fully filled with water. The oil is fully produced in this kind of block. Then the water goes to the next block and also occurs the same. So it's quite different from the previous phenomenon, because in this one, in the last one, as you remember, the water was here, imbibed or drained the oil that was here only partially, and water was already in this block. Here now you have the phenomena, physical phenomena in the same space, okay? So the water enters in the fractures and rapidly it enters in the matrix. Then it goes to the next block again. The water enter in the fractures and rapidly it imbibes the oil that is in the matrix, and then it occurs next block. So it's a kind of different behavior. So in this kind of behavior, it is easy to make some kind of average between saturations, porosity, and permeability between this block and convert this dual porosity system into a single porosity system, okay? And now you have here an example of a dual permeability behavior. So we have flow in fractures that goes, so the water goes faster in the fractures, but also there is a movement of water between the matrix blocks, okay? Because you have a higher permeability in the matrix also. So you have a huge permeability in fractures, but also in matrix, okay? So this is an example of a dual permeability behavior, okay? In a geological model, you can see that the water goes in these fractures. You can see that these small features that you have here with a huge water saturation are fractures, but also the fracture, the water that is injected is also going through the matrix domain, okay? Okay, so there are other techniques that are important are very useful to define if a fracture reservoir has a dual porosity behavior or single. So this is another example. It is an example of a well testing. So in this case, it's not average reservoir pressure, it's the well pressure, okay? So in the dual porosity behavior, fracture reservoirs that behaves as a dual porosity behavior, normally we have three stages. In the first stage is the water that is rapidly produced for fractures. That's the reason that we have this first falling from the pressure, okay? First drop in the pressure, okay? Then after the water, the oil is producing for fractures, we have an equilibrium between the fracture and the matrix, because in this stage, the matrix is feeding the fracture, okay? That's the reason that we don't have a drop in well pressure. And then we have a third stage where both the fracture and the matrix are in equilibrium, okay? So we are producing at both from in same time, matrix, and at the same time we are producing from fracture, but at the same time the matrix is feeding the fracture, okay? This is however, one thing that I need to talk about is that this is a kind of behavior that is difficult to obtain in well testing, okay? So even if the reservoir behaves as a dual porosity, it is not easy to obtain this curve. As you see here, we have the time in the log time. So this behavior is very, very fast. So even if a reservoir has a dual porosity behavior, it is not always possible to obtain this kind of behavior. So we have three criteria for choose the correct flow model: the fracture length in relation to the block length, the connectivity in the fracture system and continuity in the matrix domain, then the time interaction in matrix fracture transfer fluid compared to the fluid velocity inside each domain. We also have alternative methods to model fracture reservoirs, okay? As I talked previously, you can use a single porosity model. It's not always possible, as I talked about it, but normally people try to convert dual porosity models into a single. Why? Because the single porosity model is much faster than the dual porosity, okay? So you can use like pseudo functions. What are these kind of pseudo functions? Pseudo function is like when you try to convert something, like in this case a dual porosity model, into a single by some kind of transformation in our data, like transforming the relative permeability, for example. You can make some changes to try to put our dual porosity model as the same behavior as a single one, okay? We have a lot of other techniques, discrete fracture models, non-structured grids. So these kind of techniques, as I'm talking about, are not disponible in conventional flow simulations. However, there are some kind of people from other universities that have some code programs that can use these kind of options, okay? You can see here an example about these non-structured grids. So these non-structured grids are very, very different from what we works, okay? You can see that we have here hexagonal blocks, and here we have a fracture that is represented inside these hexagonal blocks, okay? It's very different from the structured grids that we use. Here we have a kind of example of pseudo-relative permeability curve. Here you have another example of these non-structured grids. So people pick up the discrete modeling that we have done, and they put in this kind of grids again. So you can see that the fractures are represented here in the middle and in the interface between this kind of matrix blocks. So again, this is a kind of grid that it is not possible to use in conventional flow simulators, and even in conventional geostatistical softwares. It is not possible to use this kind of grid, because in conventional geostatistical softwares, it's only possible to use corner point grids, okay? So this is a kind of resume of representative models in fracture reservoirs. So as I talked about, so this is this discrete and coupled discrete is that kind of non-structured grids that you can use, okay? You can use, but not in a conventional way, okay? You can use if you use other type of code programs. This continuum and double continuum, this is a single porosity model, and this is a dual porosity model that you can use in full simulation. This is a resume that I talked about. So when you use this kind of code programs, okay, you can have a very detailed response from or this kind of structure modeling, okay? However, the practical applicability is very small, because normally these kind of code programs, because they are not commercial use, they are not so useful to work as uncertainty, because they have a huge, very huge simulation time. They require a very huge simulation time, which is not useful when you work with a lot of equiprobable image. However, they have the capability to simulate heterogeneity, which is good. In our programs, as I talked previously, we have a lot of limitations because our fractures are upscaled to a coarse grid block, okay? So now we have talking about the base case. So until now, all things that I talked about, I never talk about uncertainties, okay? So all things that I talk about, geological modeling, upscaling, flow simulation, I only talked about a base case. What is a base case? A base case is a term that is normal to use when you construct a single realization, a single model, without uncertainty. So now I'm going to talk about the input uncertainties that we normally use in this kind of models. So before you input uncertainties in our modeling, normally it's always necessary to have a base case. A base case is a single realization of our model that passes through all steps. For you guys, that if somebody will gonna work with Petroleum, you're gonna see that before you insert uncertainties, you need to have a geological model that has been passed through all steps: porosity modeling, permeability. Then after that, only after that, you can input uncertainties. So I'm going to talk about uncertainties now, the uncertainty variables and the methods for combined variables, okay? So now is the stage for uncertainty modeling. So this is a this image came from Petroleum, okay? So as you can see here in Petroleum, you have already here what it calls base case, where is an image from all steps that we have been through. So the variables to be chosen as uncertainty, it depends on the quality of data set, number of data. So normally when we have few wells or poorer seismic data, we need to, normally we have more uncertainty in our data, so we need to find ways to spread our variability in our model in order to characterize all this kind of uncertainty that we have. So we have different type of uncertainties, okay? This kind of uncertainties came from this book, Modeling Uncertainty in Earth Science. So, however, this is only theoretical uncertainties. So we have uncertainties that are related to measure errors. We have uncertainties related to subjective forms to treat the data. We have uncertainty related to type of geological scenario, because we can have this kind of subjective forms of or uncertainty related to type of geological scenario are related to different forms that we can have for the same input data. So, like an example, you can have two geologists that says, no, we need to go in this way, and the other one says, oh, we need to go in this way. And then your starting point is quite different for two geologists. It does not mean that one geologist is wrong and that the other one is right, okay? There are two different points for the same kind of input data. You have the spatial uncertainty. So even without measure errors, we cannot use a block resolution according to reality, okay? Because as I told you previously, we don't know what is in between the wells, okay? And we never know. You also have the uncertainty on the output response, because as I talked about, we have geological model, then we need to pass through upscaling. So you lose a lot of information that comes from geological modeling. So you have more uncertainty that is related to the upscaling procedure. So we have here a lot of we have here a upscaling challenge in order to try to reduce this uncertainty that comes from geological models. So we can have a dynamic model, but normally we can have this kind of uncertainty, this doubt that is, does uncertainty on the dynamic model is a taxi to the uncertainty geological model. So this, we have here a kind of upscaling challenge. Now, here I'm going to show some uncertainty variables, okay? So in red one, these uncertainties are, these are the uncertainties that are more related to carbonates. And the black one is the uncertainties that we have in conventional scenarios. So we can have uncertainty in block size. So in fracture reservoirs, it's quite common to have uncertainty in which simulation grid block size is more useful or does as a better representation of our connectivity between fractures. We can have uncertainty in horizons distribution in carbonates, because carbonates could have a very thin layers. It's quite normal to have some kind of uncertainty in this horizons distribution. You can have a kind of uncertain intensity, fracture length, fracture aperture, fault transmissibility. This kind of uncertainty is defined in the flow simulators. It's quite normal to have uncertainty in variogram, water saturation, okay? Some of these uncertainties are defined in a flow simulator, not on geological model, like this one. Water saturation, the initial water saturation is defined on the flow simulators. Water oil contact, this uncertainty is calculated in Petroleum, okay, in geological model. Geological modeling, however, is defined in flow simulation, okay? So here I'm going to show some examples. So one of the uncertainties is the applied grid, okay? Because we never know which is quite difficult to know which is the grid that better represents our reality, okay? It's like which is the variability in samples of small scale data, okay? So because we don't have access, it's quite difficult to have. First of all, we have a limitation in the grid block size. Even in geological model, you have a minimum block size, so we lose here. We have the first information that is lost here, because you don't have, it's impossible to have a very well-refined geological grid that represents the laboratory scale and even the well log scale, okay? Then we have also structural uncertainties. So as you see here in this example, we have 3 wells, okay? So, but between the wells, so in the wells, we know that where does the horizon pass through, okay? But farther the distance from the wells, we don't know. We have a lot of possible horizons that can occur, okay? You can see that the uncertainty increases according to the distance from wells, okay? Another example of uncertainty is related to seismic. You can see that we have here the amplitude. You can see that this map of amplitude is the same as this one. But some guy thinks that the faults are here. We have faults here. But for the same input image, you can have a geologist that says, okay, no, but we can have this interpretation. So the faults could be here, not in this way, okay? So we have different, several ways to interpret horizons and faults for the same input seismic amplitude. Then we have also the doubt that is related to the uncertainty relative to the resolution from seismic, okay? So you can see here different types of characterization. Water hole contact, it's another kind of uncertainty that is we have. Here you can see an example in this on the left side. You can see an image about water saturation according to the depth of the reservoir. Okay, you can see that we have here higher uncertainty because when you don't know exactly the depth where this water saturation increases, so you don't know exactly the depth where this water oil contact is. In case B, you can see that exactly the point where this water oil contact, because you have a flexion point here where the water saturation increases rapidly. So we have, in this case, in this example, we have a higher uncertainty in case Y. Normally, fracture reservoirs, you have this kind of behavior in the right side, because due to the high permeability in fracture reservoirs, normally you have rapidly equilibrium in reservoirs. So due to the higher permeability, conductivity in the fractures, normally you have a huge transition in water saturation that gives in with a less uncertainty this water oil contact. Another uncertainty is the spatial distribution according to the number of wells. You can see here that here you have 2 wells, okay? So this is the same reservoir, okay? So you can see that you have here well number 10 and well number 2. And then you have more wells here. So now you know with more wells what is here. And then after you have the well, all wells here, you know exactly what is in, exactly with more, you know, where you know more features that are described in the reservoir, okay? So you can see that with few wells, we have a smaller sample of the reservoir, smaller number of samples of reservoir, so it's very difficult to characterize a reservoir. And if you're going to increase the wells, you have more information, which is useful to characterize a reservoir, okay? So this number of wells is important for defined spatial distribution from our layers, okay? In this case, you don't know the spatial distribution, okay? Now we're going to increase the wells and you know how does this bodies behaves between the wells, okay? One thing that the attribute that is important for this to define the connectivity between the phases, the correlation between phases is the variogram, okay? Here you can see an example. The range of variogram is 500 meters. This means that the between wells, you know that phases has a correlation, so has a variability of 1,500 meters, okay? So this is a more homogeneous scenario. So this is a range of variogram of 500 meters where you have a lot of uncertainty between wells, okay? Another kind of uncertainty is the porosity permeability functions. Normally in silice classic reservoirs, we have a huge correlation between porosity and permeability. However, in carbonates, due to the diagenetic process and the heterogeneity in this kind of reservoirs, normally we don't have a huge correlation. We can have, but you can also don't have this kind of huge correlation. So it is quite important that we input uncertainty in this kind of correlation, okay? So here is a table where it shows what are the also another characteristics that show the evidence of fractures in the reservoir that helps us to define the uncertainty that we have. Okay, so in fracture reservoirs, so normally we have a faster water cut, we have high well roots and well heights with a faster decline in productivity. We can see open fractures in plugs or borehole image. We have anisotropies in seismic attributes, and we have a dual porosity behavior in well tests. This table also shows the interpretation why this occurs, these kind of observations that we have. The precision in resolution. So we can see that the anisotropies in seismic attributes, you can see only in a portion of a reservoir. You can see the open fractures. You can see normally is related to a resolution that comes from well logs. So this is a table that helps to quantify the uncertainty that we have in fracture distribution. Okay. Now I'm going to talk about the variables, and probability curves. So the variables are the uncertainties that we have in reservoir. That could be, as I talked about, the deep in water contact, the variogram in porosity, the water saturation. So you can see for each variable, we have a probabilistic curve. So what does this mean? Because for when we needed to generate 200 images or 300 images, we don't want the same model, okay? So that's the reason we generate 200 or 300 images, because we don't want the same output model. So in that way, in order to have different models, we enter different probabilistic curves. So for each loop that we have, for each image of porosity permeability that is generated, it picks up a point from this distribution. In this case is a permeability mean, in this case is fault transmissibility, in this case is porosity average. It picks up some point of these distributions, and then it combines. This is only 3 examples, okay? Normally, like porosity average, this uncertainty that we have is a normal distribution. It follows this normal distribution. Permeability is a log normal distribution. Fault transmissibility is a linear distribution. Then it combines all these uncertainties and generates one image, okay? I forgot to translate this table to English. Then I'm gonna pass to Daniel this table translated to English, okay? So, but this table represents all kind of uncertainties that we have, not only for carbonate, but we have for cyclic gas. Normally, all kind of variables that we input in our data are here in this table, okay? So, especially the variables that are related to the static model, to the geological model, not the dynamic model. In dynamic model, we have other kind of uncertainties that in forward class, I think people are going to talk about that. So here in this table, we have the principal variables, the source of information, the probability distribution that we have for each variable that you can use if you're going to work with uncertainties, okay? So in Petrel, so now we're going to define how much image that we want, how much models we want to work, okay? In this example, we have 200 models, and then you're going to choose if you want a Monte Carlo sampling or a Latin hypercube sampling. So the main difference between both is that normally, always we use Latin hypercube. It's the most recent technique. So the Latin hypercube is a Monte Carlo also. It's an extension of Monte Carlo sampling, okay? So, however, Latin hypercube is much better than Monte Carlo sampling method, because with less realizations, it is possible to obtain a reasonable set of representative images. So the Monte Carlo, imagine that you have 100 images. If you don't have lucky, maybe the Monte Carlo will select all images in this, like in this left side, imagine, okay? But in Latin hypercube, with only like 200 images or 300 images, it is normally selects equiprobable, how do I say, equiprobably select the image from the left side and the right side, okay? So if you choose first a variable in this left side, it will choose the other one on this right side. So it has a reasonable set of representative image. This is an example of workflow for a real case that we apply in Unity. And this is a resume that we talked about of all things. So this is uncertainty workflow, okay? So first you define the number of image. Then we define the uncertainties and function distributions. Then you have geostatistical process here. Then you do the upscaling, and then you export image to Flow Simulator, okay? So this is a resume of a workflow. And however, as I mentioned before, you always need a base case, okay? You never construct a workflow before you have a single realization of your geological modeling, okay? Geological model. So then it ends here, okay? So this is a kind of example for 100 realizations. Then I think in the next class, people will gonna talk about data simulation, which is the history matching, okay? Where people will try to pick up this 100 image or 200 images that I generate here, and they try to make to filtrate this kind of image and try to match this with observed data in the wells, okay? So I don't know if you have some doubts here. If you have some doubts, also you can send an email if you want, okay?
Hello?
Hello, hello.
Hello? Do you have my voice? Sorry.
Yes, yes, yes.
Okay. I want to ask a question about the upscaling method that you told us. There is a method you call dual porosity when we have the fracture, but you say that it had some disadvantages such as fracture direction and also ignoring some kind of details which we obtain from the geological model, such as the small fracture which we have, for instance, in the matrix. So I want to know that is there any better method in order to increase the increase the reliability of the model? So probably this dual porosity model is not so accurate. So I think, is there any method in order to do
okay, because the problem is that in a conventional softwares, we have only the option of dual porosity, okay? In conventional softwares, okay? There are there are studies in parallel that study that use another kind of code programs, okay? However, it's not that kind of code programs that use that kind of grids that I'll talk about, Voronoi, that kind of grids that I'll talk about here. I think it was here. It was here. That kind of grid that I show here on the right side, it is not possible to use in conventional software. So yes, it is true that using dual porosity models is the best option that we have, but we need to consider always that we have lose some kind of information from geological models, because this kind of dual porosity models in the flow simulation, it assumes that fractures are uniform, continuous. So you lose a lot of characterization that comes from geological model. However, one thing that is good is that as we work with uncertainty, you can dilute this kind of problem in dual porosity models in our uncertainties. Can you understand? Yeah. So you can try to implement this kind of limitations into our porosity in the uncertainty, okay? Because as I said previously, we generate 200 images or 300 images. So as I said, it's not as you have a lot of images where you can try to input all these uncertainties, you can also input this doubt, these limitations into our porosity models. So that's the reason that it's important to work with a lot of image, with a lot of models, not only one, because you have not only that limitation to our porosity models, but you have a lot of uncertainties that even are related to the measure data that comes from well logs. So, but the problem is not the dual porosity models. You also have the upscaling techniques that I talked, the analytical methods, that is the Roda method, that you have a lot of information that is lost in that kind of upscaling methods. Normally, it superestimates the analytical method, the Roda method, that is the only method that you can use in the full reservoir because it's faster. Is not the method normally always superestimates permeability. So you don't have only the problem of dual porosity models, but also the upscaling upscaling that is used to convert the discrete fracture networks into a block grid property. So it's a problem, yes, but we try to input all that problems to dilute all that problems in our uncertainty models, okay?
And sorry, for instance, the dual porosity model mainly affect on the permeability because we consider the fracture. So I want to know that what is, because there was a table which you told there's all the uncertainty which we have. I think it was in the slide. So which kind of this parameter, yes, this one, which kind of this parameter can affect like fracture, or for instance, effect on the permeability?
Can you repeat the question?
Yes, the dual porosity mainly affect on the permeability because we work with the fracture. Yes, so
okay.
you say that in order to reduce this problem which we have with dual porosity, we can play with this parameter which we have here in order to make it a bit accurate, make it reliable.
Okay.
So what's the parameter here which we can use it instead of in order to have a more accurate model?
Okay, so this is in Portugal, okay? Then I could try to translate this, but the part of the fracture modeling is here. So we have several variables that we can change here to have a more accurate model. However, that is the aperture, the intensity of the fractures, the dimension of the fractures, and the orientation of the fractures. However, when I talk about these variables, aperture, intensity, that we consider uncertainty, always we consider uncertainty in aperture of the fracture that has an impact in permeability, okay? The aperture has an impact in permeability. The intensity of the fractures also have an impact in permeability. The dimension also have, and the orientation of the fracture does not have a huge impact, okay? But changing these variables provides a more accurate model, but not when we talk about accurate model under uncertainty, is an accurate model that we try to represent all possibilities, you know? So when we talk about an accurate model under uncertainty, we are not talking about a model that is close to reality, but a model that covers all possibilities that we could have in geology, because we don't know the reality. We never know the reality. So that's the reason that this part of input uncertainty is very useful. And what you talked about, that we lose information in dual porosity models, it's true, but we try to cover that issue with this kind of input variables that we have here, okay? Because as you're gonna see in the next class next week, I think it's Celio that we're gonna talk about history matching. He has the observed data, so the real data from well logs, from production from well logs, and then he can try to filtrate all models that I have passed to him and try to see which one is the best according to that observed data, okay?
Okay, thank you.
So I'm going to stop the sharing here, and if someone has more doubts, you can send me an email, okay? You can send me an email